Right now, we say, oh, the universe had a beginning, it was long ago, it was hot, it was going to have a future, and its expansion. Could we be missing something so fundamental that it's hidden in plain sight?
In the last decade, there have been probably 1,500 papers that have tried to explain the Hubble tension. And none of them has succeeded because there's so many other observations that can constrain what a model can do. But we don't yet have all the answers, and we need really accurate data to do that.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Today, I've got as my co-host, Matt Kirshen. Matt, welcome back.
Thank you, Neil. It's nice to be back.
We caught up with you. You're on a cruise. Man, you comedians you got the cushiest jobs.
I don't know if it's cushy. It's cushy to be on a cruise, I think. Telling jokes on a cruise, that's a little more work. But yeah, we were chatting about this last time. I'm on a boat right now, and then I'm on a big land tour. I'm touring with Sarah Millican, who's a great UK comic. And then off the back of that, I'm doing some headline shows of my own in clubs. So mattkirshen.com, you can stalk me. If you go to mattkirshen.com, you can find
We'll stalk you there. All right. Well, take us on a boat next time.
Absolutely. Absolutely. There's space in this tiny cabin.
And you're also a host of Probably Science. Did I finally get that right?
You did. You did. I feel like you've always known the title. I feel like
I haven't been on in like 8 years, so I'm waiting for my call.
We are talking to your people right now because let's get
excellent. Well, today we're going back into the universe, deep into the universe, and there are theorists who run around think they know what's going on, but they have to ultimately answer to the observer who's getting the actual data. And we have someone back on StarTalk who was here just 2 years ago. That's how fast this field is moving. Wendy Freedman. Wendy, welcome back to StarTalk.
Thanks very much. Yes, data is the ultimate arbiter. We can have lots of ideas, but if they don't fit the universe, we throw them out.
You are the judge, the jury, and the executioner of theorists. Is that how much power you wield, Wendy?
We need them both. The data without theory is not very useful. So it's when you have an interplay between the two that it becomes interesting.
She's being nice now because she's got to meet theorists later at the conference. I think.
You don't have the theorists ever going like, no, I think the stars are wrong. I think our equations are right.
Yeah, I spent some time at Princeton, which has a very strong history of theorists. And there's a motto there: never trust an observation unless it's confirmed by a good theory. And that's their mindset. They know they're like full of shit, but they want to say it. So, Wendy, you are a professor of astronomy, University of Chicago, in an endowed chair. Let me get that right. The John and Marion Sullivan University Professor. That's a whole other level of professorship. And in astronomy and astrophysics at U Chicago. And now, since we last had you on, you've been busy. Oh my gosh! You got the
that is true. That is very true.
The National Medal of Science. Oh my gosh! This is the highest award the country gives, the United States gives to scientists. There's also a National Medal of Engineering, and so this is
medicine.
And medicine, yes. Thanks for reminding me of that. And I was once on a committee to select the National Medal of Science. That goes through the National Science Foundation. Does it still do that?
Yes, it does.
Okay, cool. So it depoliticizes it enough so that, you can really trust that who's in there for that award earned it in all the ways one would expect. For a title.
Science is not political. It has no political affiliation. That's one of the beauties of science. It really is.
Distinguishing it from basically everything. Yes.
Yeah.
And you were cited for your pioneering work in measuring the expansion rate of the universe. Is that all? Yeah. I remember you were right out of the box with the Hubble telescope. That telescope was in part named after Edwin Hubble on the expectation it would do exactly what you did with it, was to settle the arguments, right? Could you just remind us what that was?
Yeah. So when I started in pre-Hubble, the argument at the time, there was a big debate about the size and the age of the universe. And people were arguing about whether the universe was 10 or 20 billion years old, which is a big difference. And so Hubble was built. In fact, the size of the primary mirror of the telescope was set to allow, they didn't let it go any smaller because they wanted to be able to have Hubble measure Cepheids, the stars that we use to measure distances, with that telescope. And so there was an effort, of course, because you could save costs, to cut the size of the primary mirror even further. And it was set by that to resolve this debate between a Hubble constant of 50 and 100 at that time.
Yeah, and we came up at the same time, and I just remember that being, the biggest argument anyone would ever have in the coffee lounge. People they'd split in the coffee lounge who was the old universe camp and who was the young universe camp. And of course, the actual answer landed nicely in between those two numbers, as one might have predicted with hindsight.
So they had to split the bet, whatever they were betting against each other with. They had to.
Yeah, it didn't land in either camp. It was
the table got halved.
It was like right in the middle, right? I mean,
it's interesting because there were two competing groups that Sandage and Tamon and de Vaucouleurs, who were making these measurements, and so the arguments between 50 and 100 centered on their argument. But if you look at the published values at the time, there were plenty in the middle.
Yeah, I would have never known that, because while that was going on, I was at the University of Texas, which was home base for Gerard de Vaucouleurs. He was Mr. Young Universe, right? And so, did I get that right? He had the Hubble constant of 100.
He had a high Hubble constant.
Yeah. So it was. So we were not allowed to think outside of his box there.
That's okay. I was at the Carnegie Institution with Alan Sandage, and that was a very interesting time. He kind of disagreed.
Yeah. So thanks for solving that. And also, just this year, named Time Magazine's 100 most influential people in the world. Congratulations on that. When was that announced?
Oh, I'm trying to think of when it was announced. So
it's already happened. You already had the celebration?
Oh, yes, we did. We had a nice.
Wait, so you came through New York, and you didn't. You came through. You
came through New York. In fact, your people checked with me. Was there a date where I could do this?
My people were on the case. Okay.
Yes. But it didn't work out.
All right.
But yes, it was a lovely event, not what your usual scientific conferences are like.
No, yeah, it's a celebration. Yeah, it's good. And this paper that you hinted at when I had you in New York for the Asimov panel debate, your paper solved what I think you're going to give me details here, but if you just believed the newspaper headlines or the clickbait in news websites, you would think that all of cosmology was in crisis and we're all ready to just cry in our, cry in each other's laps about how to solve this. And you landed at a place that seemed like, we got this, and we don't have to give up the Big Bang to do it. So the Hubble tension, remind us what people are calling Hubble tension. Just tell me about that.
The Hubble tension is what's arisen in the last decade or so. We make measurements of the Hubble constant, the current expansion rate, locally using stars like Cepheids. We also use red giant branch stars and other ways of doing these measurements tied into type 1a supernovae, these bright.
Right.
supernovae.
So all of these in this list that you mentioned, these are yardsticks, standard candles, right? So because not every object serves as a way to know how far away it is, right?
That's
so right. There's only a handful, and they're cherished, right?
They're rare stars. They're, for example, Cepheids, when we go and try and discover them, like we did with Hubble, maybe 1 in 1,000 stars that we measure turns out to be a Cepheid. So they're rare, but they also have a signature, and in the case of Cepheids, discovered by Henrietta Leavitt, that the brightness of the star correlates with how fast it's varying in its brightness, so-called period luminosity relation. And we can use that relationship to determine the distance.
So Henrietta Leavitt, that's a full 100 years ago or more, right?
That's right. Everything that we have done since then rests on her work. And
what's kind of cool is she get to make those discoveries because the men wouldn't allow the women to do to work. What's the most tedious work that is possible in the field? And it's like classifying stars and measuring the brightness in their spectra, and that's where all the discoveries happen. So
that's right. And she was astute enough to notice, not only were these stars varying that she was finding in the Large Magellanic Cloud and the Small Magellanic Cloud, but there was this correlation. The brighter stars were taking longer to go through their cycle of variation. And this is the basis of what Hubble's discovery, that there are other galaxies outside the Milky Way, that the universe is expanding. We use it for the Key Project. We use it today. And she fell into obscurity. She was kind of lost in the dustbins of history for a long time, but we're recognizing her now. And I think that's, the New York Times actually wrote an obituary about her in 2024.
Okay.
Died, I think, in 2021.
It was a catch-up obituary. Right.
Did they write it fresh, or did they just find it in an old drawer from?
No, they wrote it fresh. They're making an effort to try, and they're recognizing that it wasn't just men who did things in those days. Particularly.
Yeah,
there were other
reconciliation project. Yeah. Very good. And I'm happy to report that at least in our era, Wendy, the textbooks that we taught from and learned from, there was good mention of the women of Harvard at the time.
And we now refer to the Leavitt Law, and that there was a meeting at Harvard in 2008, which was the centennial of her first publication on the PL relation. And we decided that it would be appropriate to rename it the Leavitt Law. I had actually been doing that for a while.
Instead of the period luminosity relation, right?
Yeah. Okay. Yeah, there's a Hubble law, there's a Hubble constant, there are Hubble galaxies, different morphologies and classification and so on. And everything rests on the PL relation.
I'm all in. Take us back to the Hubble tension. And how much of how tense was it in the room? Or how were you in the room when it happened? I don't like that word tension. I mean, in science, if things don't agree, that's kind of fun. I just got a sense that it was more a marketing ploy to get clicks on a website. But maybe you have a different view as one who's in the middle of fixing the tension. Where did you come from there?
So sorry, just to be clear, for me to answer, it is actually meaning tension in the common English sense. It's not using tension in some kind of physics sense. You're actually using it like awkwardness or discomfort.
Well, it's signaling a discrepancy between what we're measuring locally when we use these stars like Cepheids or red giant branch stars and supernovae to measure the Hubble constant, the current expansion rate today. And when we compare that method with what you infer from the cosmic microwave background, the background radiation from the Big Bang, you can measure these very small fluctuations in the temperature and also the polarization of the background radiation and fit those with the spectrum with what we call the standard cosmological model. And that's been now in place for a quarter of a century. And when you do that, this is a predictive model. It tells you how the universe will evolve. And it tells you that the expansion rate today would have a value of 67 with a very small uncertainty of less than 1%. And when we use Cepheids with HST, we get values more like 73. And so that's a rather small difference compared to 50 and 100, where we started off when Hubble.
Yeah, I would have been I said, let's go have a beer. We're good here. That's what I would have said.
I think it would have been appropriate to relax a little bit and have at least a day to celebrate things that got closer. And there are always crises in cosmology, and I think it was a very rare time around 2001, 2003. So our HST Key Project results came out in 2001. We got a value of 72 with an uncertainty of 10%. And then WMAP, the Wilkinson Microwave Anisotropy Probe, first measurements of all sky in space for the microwave background, got a value of 71. So it looked pretty good. And the acceleration of the universe had been discovered. The age was something like 13.7 or 13.8 billion years. And wow, here you are measuring locally using stars, and you're using a redshift of 1,100, 380,000 years after the Big Bang. You're making these tiny measurements of the temperature differences. And boy, they agree pretty well.
So the two puzzle pieces fit by making local measurements and distant measurements. So that pretty much tells you're onto something there. Nope, that's lame. Ready? Do you harbor questions about the universe? Some long-held bit of cosmic curiosity lingering within you, or questions about anything at all, you can become a Patreon supporter of StarTalk. You have access to our exclusive question line on our website. Those are where we draw our questions for our cosmic queries.
Some of the most extreme objects in the universe.
StarTalk is a work in progress where we, every month, come up with some new way, some new idea, some new understanding of how to bring the universe down to Earth. We could not do that without your support. Thank you. And as always, keep looking up. So, Wendy, if you can remind people, when you just say the number 73 or 67 or 70 or 50 or 100, that is a measurement of precisely what?
That is a measurement of how fast the universe is expanding at the current time. It has units of inverse time. So it is also a way of getting at the age of the universe. It, in detail, is kilometers per second per megaparsec. So when we talk about a Hubble constant of 70, we mean 70 kilometers per second per megaparsec.
So for every megaparsec an object is away from Earth, from our galaxy, it'll have a recession velocity of 70 kilometers per second.
Yes, and so
when you add another megaparsec of millions of parsecs, then there's another 70, and this just keeps adding.
That makes it so the further away you are, the quicker it's moving away from you.
Exactly.
The rate at which that's happening
was Edwin Hubble's original discovery. What he showed is the farther away a galaxy is, the faster it's moving away from us.
And so those units, he first plotted that, and so we named the unit of that. So it's basically the slope of that line, I think, right?
That's exactly what it is.
Yeah.
Slope
Okay.
of that correlation is the Hubble constant.
Okay, cool.
And that is the expansion rate at time t equals 0 now.
Okay. We're fitting these measurements into a base model of the universe, right? I mean, right now we say, oh, the universe had a beginning. It was long ago. It was hot. It was going to have a future and its expansion. Could there be is this like epicycles? Could it be like epicycles where, the planets, they're on these epicycles and they do this, and now we can explain everything? Could we be missing something so fundamental that it's hidden in plain sight?
We could be missing things. I think that's what is exciting about these particular, or the time at which we're making these measurements, is that we're pushing the boundaries of what is possible to do with these measurements and to test the framework. So we talk about a standard model of cosmology. That's a model that has it's a universe expanding. It has dark matter, where you have the ordinary matter that we're made out of is only about 1/6 of the total matter in the universe.
So we don't matter, is what you're saying.
We do matter.
A sixth of you matters.
A sixth of you matters.
And the other part is not telling us what we're about. But anyway, we do matter. We're the luminous stuff.
Oh, yeah,
and
there you go.
The luminous stuff shines a light on the dark stuff. That's how we learn about it.
You don't just matter, you glow.
Oh, very nice, Matt. I like that.
2/3 a form we call dark energy, which is causing the universe to accelerate. So there's plenty of room, to get back to your question, for things that we don't yet understand, because we don't yet know what the dark matter is, despite decades of trying to detect it. We know what it does to the luminous matter. We know that it's there because of its effects on the luminous matter, but we don't know what it is. It's most probably a particle left over from the Big Bang, and there are lots of efforts to try and discover it, but that has not occurred. And the dark energy, we have no physical understanding. There's no physical theory that can explain what the dark energy is. So yes, there's lots of room for us understanding this standard model. So there could be cracks in the model, and maybe this discrepancy is one of the things that's pointing to something missing from the standard model.
And let me emphasize something that you just briefly mentioned. So we started our careers with a Hubble constant ranging from 50 to 100. And we resolved that, and we met somewhere in the middle. And we knew that was a problem, but the uncertainties were pretty high back then. So one might even say the uncertainty bars overlapped. So that you say, if the answer is anywhere, it's going to be somewhere in the middle. Now you're saying we have two results that are much closer to each other, yet the uncertainties are so small, there is no chance of them overlapping. So something has to give.
So either this is really interesting and we're learning about some fundamental property of the universe, or we've underestimated our uncertainties.
Okay. I'm going to bet on the second one.
So that could mean that we'll learn something about astrophysics, about the properties of stars. We're going to learn something about supernovae or Cepheids or something interesting astrophysically, but not necessarily telling us about cosmology.
Would you have used the word crisis?
Would I have used the word crisis? No, I don't believe it's a crisis.
Right.
Not in my opinion.
Yeah, that's my opinion as well. But your opinion is way more valid than mine in this space. So we're going with your opinion on this for sure.
I would have used crisis for that if anyone wants to survey me. I'm
You a crisis camp?
Yeah, is my opinion valid? Where's my opinion rank amongst?
Yeah, fortunately we don't vote on these things. Empirical evidence, the data thing again. It's important.
Why doesn't someone with almost no science training weigh as much in this as a leading scientist? It's just not fair.
It's not a democracy. That's the problem. It's not a democracy. So then, Wendy, you step in once again and come up with some sensible understanding of what's going on. Could you update us on that recent research paper of yours? And who are some of your colleagues on that?
Yeah, so we have a small group, which a really nice group. It's small and efficient.
Excellent. That means you get more done. And correct me if I'm wrong. Any good collaboration, everyone on the team brings their own special awareness and understanding and specialty to it.
That's
Otherwise,
right.
You just have redundancies, and there's no point for that.
Yeah, and everybody is working really hard. It's our proposal, the proposal that we put into James Webb Space Telescope, so this is where we're focused now, was to use 3 different distance indicators. The Cepheids that we know and love, the tip of the red giant branch, which is a method that Barry and I and collaborators have been working on for many years, and in the last decade or so have really refined it in terms of improving its precision.
So this is a section on the Hertzsprung-Russell diagram, which doesn't really clarify. If you say the tip of the red giant branch is a special place on the Hertzsprung-Russell diagram, now we're all clear. So what you're saying is, as stars age, they change in properties, but there's a certain property that they take on that has a good that an ensemble of them will have a consistency that you can rely on, that you can see at great distances. Is that a fair way to characterize?
Yeah, that's fair. These stars, so our own sun will become a red giant later in its evolution. And so these are stars that have masses comparable.
Matt, it's in 5 billion years, so don't worry about this one.
Don't worry. Yeah.
I'm busy that day.
You got a gig that day. All right. We'll delay it.
I can move it. If it's important, I can move it, but I'd rather not.
These stars have a degenerate core, which packed very, very densely, and they've exhausted all the hydrogen in the core, so that most of a star's lifetime is spent burning hydrogen into helium in its core, fusing hydrogen into helium. And then when the star contracts, it's not hot enough to start burning helium, and that would happen in a more massive star. So it's burning hydrogen in a shell and putting more helium onto the surface of this core. And when the core reaches a certain mass, a certain temperature, then there's a thermonuclear runaway. So suddenly you can start helium burning, and it releases a lot of energy very, very quickly. And then the star settles down onto another obscure term in the Hertzsprung-Russell diagram, what we call the horizontal branch. But the point is that these are now fainter stars. And the position at which this, what's called core helium flash occurs at a very well-known luminosity. And so what that means is we will observe stars in different galaxies, see how
Another
bright
standard candle
near
for
to
you.
be. It's another standard candle. Calibrate them locally, and then use the inverse square law to get the distance. So there is a very clean method.
And allow me to offer an apologia to our fellow chemists. When astrofolk say things burn, we don't mean what you mean. Okay, we mean by that. yeah. Hydrogen burning. You said it. You said it briefly in there, but then you went back to burning. It's hydrogen fusion.
Right.
But we're very sloppy there, and I apologize to chemists. It's your
word. So if you need to put that out, do you?
I think that
Sorry, I spoke over you, Daniel.
Bigger insult is that we consider pretty much everything heavier than hydrogen and helium to be a metal.
Oh yeah, we call them metals. Yeah, we're bad with our chemistry, but we're sticking with it. We're stubborn in this regard.
If you've got the hydrogen burning in a star, do you if you need to put that out? Do you is it a water hose or do you use a blanket or foam? Which of the three extinguishers are we talking about?
Don't do this at home. Don't get close to this.
Go the other way. All right, so you're working on. I interrupted you quite on purpose, but you were working on several methods of distance determination. Yes.
So we're using the James Webb Space Telescope to measure distances to galaxies using these three different methods: the carbon stars, the red giant stars, and Cepheids. And that will allow us ultimately, and we're partway through this project, to determine how well we've measured the distances, right? Do all three methods agree really well? Is there a large spread in the values? Do two agree? One's an outlier. This will give us a chance to say, what are the overall uncertainties?
Got it.
And those nearby galaxies that we're observing with JWST, those galaxies then tie into the distant universe where we can see type 1a supernovae well out into what we call the Hubble flow.
So you're the base of that pyramid. They don't know the distance to the supernova any better than you would know what its foundation is. Is that?
That's right. We can measure the relative distances of supernovae. We can see which ones are farther away, but we don't know what the absolute distance is.
To calibrate them. Okay. So you, not to put words in your mouth, but you think in the results of your work, you will show perhaps that people were overzealous in their small uncertainties that they were reporting. And maybe the uncertainties are a little wider where they would then overlap, and then it's not a tension, and there's not a Hubble crisis and a cosmological crisis, and we can all go out and have a beer.
Yeah, I think, to quote the late Carl Sagan, extraordinary claims require extraordinary evidence. And I'm not yet seeing extraordinary evidence. So our result, we're getting a value of about 70. And that agrees very well with what we got from Hubble using these red giant branch stars. And I think the uncertainties still, they're not at the level that come out of the cosmic microwave background measurements. The cosmic microwave background measurements have a precision of better than 1%. So they've really set the bar very, very high. And that's just not possible yet, to make measurements at that level of accuracy when you're trying to use stars that are millions out to hundreds of millions of light years away.
I didn't appreciate that. So you're saying the cosmic microwave background measurement determination of the Hubble constant is the gold standard against which other measurements have to match. No one thinks that there's a problem with those measurements at all. Is that correct?
So far, there is no indication that the measurements themselves are an issue. So they're the measurements from the Planck satellite, this European satellite, which is still the gold standard in the field. It's all sky. And there are two groups on the ground, one in the Atacama Desert and one at the South Pole, that in fact came out with very recent measurements, and they're very much in agreement. The issue is, in order to get the Hubble constant from those measurements, you have to have a model to fit the data. So this is the beauty of this. Given the model, you predict what the Hubble constant today should be. How do you test the model? You measure the Hubble constant today. So if you can measure it with enough accuracy, not just precision, but accuracy.
Tell us the difference between those two.
So, if you have a coin and you flip it, if you do it a few times, you might get more heads than tails. If you do it enough times and your coin isn't weighted in some funny way, it's going to come out 50-50. And the more times you make the measurement, the more accurate your measurement is going to be. But then there are other kinds of errors that no matter how many times you make your measurement, you're still going to have what we call systematic errors. And an example of a systematic error would be, we know that stars like Cepheids form in the disk of galaxies where there's astrophysical dust. So dust, just like here, if you're looking at a mountain far away and a dust storm blows up, you look at the sun or you look at the mountain, the sun's going to get redder and fainter. Same thing happens if there's a fire, right? If you've seen a red sun, that's what happens when we're looking at these Cepheids through the dust. They get redder and dimmer. And so if they look dimmer, you're going to say, oh, this is farther away. If you haven't corrected for it, no matter how many times you make the measurement, you're still going to have an error. So there's this distinction between precision and accuracy. And if you only use one method, if you're only using the Cepheids, you're not going to be able to tell what the systematics are. So you have to use, that's my strong feeling. That's what drives my research, is you have to do this in more than one way.
So, Wendy, you're thinking that systematic errors are prevalent within these measurements because they sound all precise and everything, but they could be they're precise yet wrong.
That's exactly right.
Yeah.
Yes. And I think certainly historically, that's what we've seen in these measurements. It's always the systematics that come back to bite you. And often they're unknown systematics. We know about the dust now. We can correct for it. But what are the things that we don't yet know about? And could there be errors in the calibration and in the calibration of the dust laws? There are lots of potential gotchas.
And you've got an advantage there because people who come to this as cosmologists, they don't know anything about stars, as far as I can tell. You have a huge background in sort of traditional astronomy, where with stars in a galaxy, the dust, the reddening, the magnitude of all of this. And so that makes you particularly potent on that frontier.
Well, I think, astronomy is different than physics. Astrophysics is different than physics. We don't have a laboratory where we can go in and we can work with the equipment and we understand the equipment and do tests that we set. We're working with these stars that are far away, that have metals in their atmospheres, pulsating stars, exploding stars. If we look at the supernovae, we don't understand yet, although there's some interesting hints that maybe we understand one of the mechanisms for exploding supernovae. But there's scatter in the relation for supernovae, and the supernova magnitude, supernova luminosity depends on the color of the star, how fast the supernova, how fast it's declining, the mass of the galaxy, which surely has nothing to do with the supernova itself. It's a proxy for something else. And then there's additional leftover scatter, and different groups have different calibrations of the supernovae. And so when we're comparing our local observations with the cosmic microwave background, where it's clean and what is referred to as linear physics, and there are different groups that are getting the same answers, and with a precision, again, of better than 1%, the onus is on us, I believe, locally, to really show that we have overcome the systematics in using these stars.
You kept referring to today's value of the Hubble constant. That implies Hubble constant had a different value in the past. So then why are you calling it a constant?
The Hubble constant refers to a Hubble parameter at the current time, t equals 0, h 0. And actually, the Hubble parameter, the parameter that governs the evolution of the universe, changes with redshift or with time. So it's a
little bit of a misnomer to call it a Hubble constant.
Yeah, it's confusing. It is the value of the Hubble parameter at the current time.
So you're messing with people again, just like when you talk about hydrogen burning and all the metals on the periodic table. So Wendy, if people are looking at different parts of the universe, at different objects and getting different Hubble constants, why can't the universe just be different in these different sections? Why must the whole universe be giving you the same answer to that question?
So several different things to unpack in your question. You could ask, is there a concentration of mass locally so that, or maybe we live in a giant bubble, say, and that
Matt lives in a bubble. I'm trying to get him out of the bubble.
So maybe the expansion rate locally is higher because they were being pulled to this mass concentration. And that was talked about a lot at the time when we were arguing about 50 and 100. Maybe the mass distribution wasn't well mapped out. But now there are literally thousands of supernovae that have been measured. You can measure, really well across the sky, and there's no evidence that it is varying locally from region to region to the percent level. As I said, the universe does evolve with time, and we don't know. As I said, also we don't understand what the dark matter is yet. We don't know what the dark energy is. So there's lots of, I think, the tension is a tantalizing idea that maybe this is additional physics because we don't yet understand the nature of the dark energy. But it's very interesting because in the last decade, there have been probably 1,500 papers that have been written and posted to the Astronomical Archive that have tried to explain the Hubble tension. And none of them has succeeded. And the reason is, in large part, because there's so many other observations that can constrain what a model can do, and the effect that it would have that we would be able to measure with measurements today or with the microwave background or so on and so on. So this is where we are at the forefront. We're trying to push the limits. We're trying to understand what is governing. What are the constituents of the universe? How is it evolving? But we don't yet have all the answers, and we need really accurate data to do that. And so I would say it's not that this is completely solved. I think we need to do a better job showing that there is a significant tension. And as the data improve in future, this is going to go one way or the other, right? Either the signal is going to improve or it's going to fade away. And one of the examples is recently with measurements of the microwave background, there was a tiny little hint in the measurements from the Atacama Desert, the cosmology telescope, in an early release of theirs that maybe in the polarization there was a hint of what might be due to evolving dark energy that could explain the Hubble tension. But they just come out with a release with much more data, and the signal just disappeared. It was noise. If it had been real, it would have been really apparent, but it went away. So that's what happens. You see things at a level of significance that we call 2 or 3 sigma. 5 sigma is supposed to be the gold standard. It would be a 1 in 1.7 million chance that it isn't correct. I just don't think we're at that level yet. We have more work to do.
So this bit about the change in the dark energy properties that made serious headlines when that came out.
Well, this is different. This is an early dark energy that would have explained the Hubble tension. Evolving dark energy, it still could be evolving. And again, this is early data. There's going to be a lot more coming in the next.
And just to recast something you said a moment ago. But tell me if I haven't oversimplified it. These 1,500 papers of people trying to explain the Hubble tension, they'll come up with an accounting for it, but then it breaks something else that we know very well would not be the way it is.
That's right.
If their idea were correct. So it's quite the Rubik cube. You can't just explain one thing without affecting 100 other things that we know very well.
Yeah, that's right.
So this is part of what gives us confidence in the overall Big Bang scenario for the origin of the universe, because it's supported in so many ways with so many different branches of astrophysics. And so, yeah, this is actually a cosmic queries. Matt, you didn't tell me this was a cosmic queries. Why didn't you tell me that?
Oh, because I don't feel like I have any seniority on this show.
Okay, I grant thee astrophysics powers in the flow of content.
I'm honored to be your knave. Does this make me a knave? I don't know. I'm not
Squire. You're Squire. Yeah.
Squire. I'll take that. I have to put your mortarboard and your gown on you and just send you off to battle. So yeah, there's some great questions as always sent in by your Patreon subscribers. So Hannah Cantley from the City of Roses, Portland, Oregon says, could the effects of dark energy on space-time geometry potentially arising from entropic forces complicate our ability to measure distances to distant galaxies, especially considering that their apparent recession speeds may exceed the speed of light due to the expansion of space, and this might necessitate new models and techniques to account for these influences?
Yeah, Wendy, is dark energy messing with you? Could it be messing with you? If you don't know what it is, you can't say that it's not messing with you. How about that?
Well, I think that's fair. I think we know very little about what the future evolution of the universe is going to be. Will dark energy decrease with time? Is it constant? Is it Einstein's cosmological constant? And I think these are empirical questions right now because we don't have a good theory. And ultimately, we do hope that there will be a fundamental theory. But right now we're being guided by observations, and the observations that it's decreasing with time, evolving with time, and getting less. There's less of it now. That's new, and there are many more experiments on the drawing board that will test that, and we'll see how it lands.
Now, isn't there a dark matter telescope coming online?
It just did. That's the Vera Rubin telescope.
Oh wait, what's the Nancy Grace Roman telescope? What's that one?
That's a survey telescope. It's a NASA telescope in space.
What is that? That's didn't they call that the dark matter telescope or not?
Originally, the Vera Rubin telescope. It started out probably 30 years ago, almost.
Oh yeah, okay. But we just did 2 shows on the Rubin telescope, so we're up on that. Matt, what do you got next?
Lissa says there is still a gap between how fast the universe is expanding based on nearby measurements versus predictions from the early universe. Based on your work, do you think this means we're missing something in how we measure it, or could it mean our current model of the universe needs to change? And Alyssa also says, thank you for being a badass woman of science.
I think that's precisely the question we want to answer. And I think, I personally am open to it coming out either way, but I have to be convinced by the data. And at the moment, I am not convinced by the data that there is this crisis and that there's something broken in our standard model. So time will tell.
Yeah, and if I can add to that, I think most occasions in the history of science where there's been some discrepancy, just a better or more data resolved it. And every now and then it requires new physics. So I see what you did there, Wendy. You're saying you're not ready to have to require new physics because the data to be obtained still needs to be refined. So Wendy, there's great precedent for people such as yourself to take that view of the world, but you don't want to miss new physics.
That's right. That would be very exciting. I would love to see it, but I want to be convinced. And I'm just not at a point where I could be convinced.
Good. All right. Matt, what's next?
All right. Jamie and Sabrina from Transylvania ask, in the future, when we are all zipping around the universe on starships, how will we keep track of the expansion of the universe? How will we find our way home when home isn't where we left it?
Oh, I love it. You got a coordinate system for us in the future, a GPS for the cosmos, Wendy?
I don't think I'm going to be around that time. We can do that. But I think, what we're measuring in our own Milky Way galaxy, if we were to go to Andromeda or other galaxies in our local group or beyond, we would be measuring the same thing. I think the frightening thing to think about is in 60 billion years, if you're worried about future, the acceleration of the universe, if it continues, if it doesn't, the dark energy doesn't decay, then we won't see other galaxies and we won't have the chance to make the measurements that we're making today. So I think that we're living in an interesting time, but we don't have to worry in the same way Matt doesn't have to worry about the sun. It's going to be a long time in the future.
Or if I could add a sort of more obscure but possibly relevant example, in the old days when they had their first generation of seaworthy chronometers, very important in navigation and finding your longitude around the world. Davis Sobel's famous book, Longitude, really blew open that field for the public.
Book, yeah.
And she is one of our, I think she was the very first StarTalk interview. Oh my gosh. Deep in our archives, find Davis Sobel, the author of that best-selling book. Anyhow, what I understood they did, they would make these chronometers and finally close the back, and all the springs and the thing, they'll all be in there, and then they check it, and it would either gain time or lose time to the standard. Rather than reopening the clock to try to, quote, fix it, they accurately measured the rate at which it was increasing time or decreasing time. And that became an equation to correct the time they read during their voyage. So something similar to the question is, if you know the expansion rate and you know how long you've been gone, then you can extrapolate through where you know we should have been. And then you still can find there's no place like home. So bring an equation with you for the expansion of the universe and then go backwards along that path, and you should be able to get home. That's what I'm thinking.
Well, while we are talking about distances, I think we have time to squeeze in this question, hopefully, from Chris from Marlborough, New Jersey. Says, dearest Dr. Tyson, Dr. Friedman, and any esteemed guests, I'm going to count myself as esteemed in that case. Chris asks, would the way you conduct your work change if we found out definitively our universe is infinite or finite in size? Also, which option do you find more plausible? Thank you very much, both of you, for your stewardship of cosmic curiosity.
Ooh, I love that sentence. Beautiful.
I'll say it wouldn't change how we would do our work. I think we would continue to observe the universe, measure it, and see what's out there. So that would not change. You can answer the other part, Neil.
No, how would you feel emotionally if the universe were finite versus infinite? How about that?
And which do you believe is true?
I find this interesting, these kinds of conversations. So I think I'm not emotionally attached to one kind of universe or another. I really have no emotional.
That's a healthy posture in science, for sure.
And so I don't have a feeling about it. But I remain intensely curious about what it is, and I love the process of science that allows us to ask these questions and then go out and make measurements and try and answer some of these questions. But I have no particular favorite child of a universe.
Okay, yeah, I'm leaning infinite. I'm all into the infinity, just because that's more fun. That's got to be more fun in an infinite universe. Yeah. And Wendy, do you remember there's a scene in the film 2001: A Space Odyssey where towards the end, where it gets kind of psychedelic, one of the captions of the scene is to Jupiter and beyond the infinite, or something. They get infinity in there, and
that
I forgot
the bell. Yeah,
I forgot the exact quote. And just, I think it's fun to get people thinking about infinity because we know we can't wrap our head around it, and so it keeps you nimble.
Yeah, real time in these things, answering things like this. I just don't want to get tangled up in, yeah.
But it is fun when you first learn calculus. You have to really cozy up to the concept of infinity and infinitesimals, like the opposite of infinity. So
where they're going in these questions, I just never.
I'm still on Zeno's side, and I refuse to believe motion is possible.
Oh, Zeno's paradox? Yeah.
I'm firmly
you do get to where you're going.
Yeah.
You do get to where you're going. So, Wendy, this has been a delight to have you back. Oh, my gosh. Congratulations on the National Medal of Science. And I think I get to tell people it comes with no money. It's just a medal.
That's correct.
But another visit to the White House. We've met there a couple of times.
Yeah, we have.
And it's always good to bring some science into the White House. The country's better off anytime that happens. So our health, our wealth, and our security are enhanced.
All of the above. Yeah.
All of the above. All right. And Matt, good to have you on again.
Thank you.
Enjoy your cruise.
I will. It's so far so good. We're getting away with it so far.
Okay. And we'll find you online at Probably Science. Once again, this has been StarTalk, a Cosmic Queries edition, but filled with updates on observational cosmology, giving us our understanding of the universe that we so desperately seek. I'm Neil deGrasse Tyson, your personal astrophysicist, as always, bidding you to keep looking up.